Hello and welcome. In this video I'm focusing on the intermediate value theorem and some related results. So these are again similar to what we were talking about with the extreme value theorem. We had a continuous function from an interval to the reals. And each of these results are going to appear quite reasonable. They're intuitively true, but will require a little bit of care in order to prove rigorously, just like any related statement would be. So for the intermediate value theorem itself, in the notes this is theorem 4.2.5, we're saying that I be an interval. I'm focusing on 2 points, so A and B, as indicated over here in the graph. And the intermediate value theorem tells us that for any point which lies between the image of A, so f of A, and the image of B, so anything along here, such as y0 indicated, then there exists at least one, there exists some x0 whose image is equal to y0. Now in this case we have 3 possible places, but in general all we're saying is that there exists at least one. And of course that's not going to capture all of the possible points of f on A, B in general. In particular, anything beneath f of b in this graph won't be captured by that. In order to prove this, I'm going to relate it to a much simpler statement, known as Bolzano's theorem. So in a similar vein, we take a function from a closed interval to the reals. We have this condition here that f of a multiplied by, so this is not, they're both negative, the product of the function at each endpoint, f of a times f of b, is negative. So with that condition, we're really just saying that either f of a is positive and f of b is negative, or vice versa, f of a is negative and f of b is positive. And so I'm thinking f of a is greater than y0 and f of b is less than y0. So they're on either side of this line. So in particular, we're interested in f of x is equal to 0 in this case, but previously it was this general y0. Otherwise, it's telling us roughly the same thing. So if we have such a function, then we can always find some point in the open interval such that f of x0 is equal to 0. We have an open interval here because we can discard the endpoints. We know that the product is less than 0, so we know that neither f of a or f of b are 0. So as an exercise, you should show that Bolzano's theorem is equivalent to the intermediate value theorem, at least in the same setting. So a lot of the work that you'll do here is similar to what I've just indicated. It's going to be about shifting this function. So if I have the graph as indicated, then really I'm thinking of bringing this down so that my target at y0 is actually just 0. And so I can do that by subtracting a value from the function, or to go the other direction, adding a value to the function. And otherwise there's just some work to go through and verify that each statement implies the other. Here, however, I'll focus on a proof of Bolzano's theorem. The actual proof is not that much different from what we would have for the general intermediate value theorem, but we're just carrying around a little bit less notation, so hopefully it's more clear. To make things even easier, I'm going to assume that f of a is greater than 0, and then because the product must be less than 0, that tells me that f of b is less than 0. This is just so that I can have a clear picture in mind. So a similar function to the one above, and we're asking the question, show that there exists some x0 such that the function f of x at x0 is equal to 0. Now, in order to do that, we're going to define a set. We know that f of a is positive, and we're going to define E to be the set of all elements in the interval such that f of x is positive. So we know that this is non-empty because f of a is an element of E, and we know that it's bounded as it's a subset of the bounded interval AB. So graphically, if I focus just on this, it's not going to be precise, but it's good to keep a picture in mind. So these are the points where the function is positive. So it will include f of a, it will include a, then it's negative in this region, and afterwards it's positive again. So the highlighted intervals, 2 disjoint intervals, are going to be the set E in this case. And we claim that the supremum of this set, so let me give it a name and call it S, f of s is equal to 0. And that will complete the proof. I've already justified why the supremum exists. We have a non-empty subset which is bounded, so it has a supremum. By the approximation property, there exists a sequence xn with each term an element of E and converging to S. So here's where we're going to use continuity again. We've generated a sequence, we know it exists by the approximation property, and because f is continuous, when we apply f to this sequence, then we will get another convergent sequence, and that tells us something about f of s. So by continuity of f of xn converges to f of s. But we know something about f of xn. Because xn lies in the set E, we know that f of xn is greater than 0 for all n. And by taking a limit, by looking at the limit of this sequence, we get that f of s, although we can't say it's greater than 0, we can say that it's greater than or equal to 0. So already that's getting close to something that we want. We want f of s to be equal to 0, but now I know that it's at least non-negative. So there are essentially two cases that we're interested in. First of all, if f of s is equal to 0, then we're done. We wanted to show that such an s existed. However, in the other case, if f of s is greater than 0, then we can use the continuity of f to show that the function is positive in some interval around s. And to make that precise, what we're saying is that we can find some epsilon greater than 0. This may be very small, but nevertheless it exists, such that f of x is positive for all x within epsilon of that value of s. So I'll leave this as an exercise. Okay, so assuming this result, assuming the result of this additional claim in the exercise, what we have is that f of s plus, so for all x inside this interval, we have f of x is positive. So in particular we have f of s plus epsilon over 2 is greater than 0. But of course, s plus epsilon over 2 is greater than s, strictly greater than s, which contradicts the fact that s was the supremum. So my assumption here is false. I have a contradiction. My assumption here was if f of s is greater than 0, so that leaves me with the conclusion that in fact f of s is equal to 0, and so this is done. Although it does require this exercise in the middle. As a first application, actually of Bolzano's theorem, but equivalently the intermediate value theorem, we have essentially a fixed point of a continuous function from an interval to itself. So a fixed point, hopefully the name is fairly clear, but a fixed point for a function, mapped from some interval in this case, but it could be more general, is just some value for which the function returns that value. So the identity function has everything as a fixed point, and the function x mapping to x plus 1 has no fixed points. So often when you're studying a function, this is an interesting property. Does the function have fixed points? So in this example, I'll show that a function from a closed bounded interval, so 0, 1 in this case, to itself has a fixed point. Now pictorially, this is a little cube, so it's mapping from a fixed 1 unit interval to itself, so I can pretty much just visualize it. And again, this will just be a rough graph, as I tend to do. So we have 0 to 1, and it maps somewhere inside this box. Or at least the graph of the function lies entirely inside this box. And so the idea is that you have a fixed point of this function if ever it crosses the diagonal from 0, 0 to 1, 1. So drawing in a dashed line for the diagonal, if the function ever crosses this, then you have a fixed point. If it starts off f of 0 is 0, well, there's your fixed point. Or if it ends with f of 1 is equal to 1, that's again a fixed point. So you're done. So you assume perhaps that f of 0 is positive and f of 1 is less than 1. And then your continuous function, with again the intuitive sense of continuity here, we just draw some graph But if I can't cross this dashed line, I'm forced up into this corner. But I just said that the function was not 1 at this point, so somehow, in a continuous manner, I have to get back down, but then I'm crossing that line, however I do it. So rather than stating a new theorem, I simply try to relate this to the results that I already have. So in particular, Bolzano's theorem. So I define a new function to be f of x minus x. So now a fixed point of x is a value, f of a is equal to a. So plugging that in, we will get that g of that value is equal to 0. So any 0 of g is a fixed point of f. And Bolzano's theorem tells us about the possible existence of a 0 of a particular function. So note, g has the same domain as f, so it takes in value 0, 1, but has codomain minus 1 to 1. So the reason is that, of course, the image of 0 might be anywhere between 0 and 1, and the image of 1 is anywhere between minus 1 and 0. We have g of 0 is equal to f of 0 minus 0, but that's just f of 0. And that's greater than or equal to 0, because again, f maps to 0, 1. And we have g of 1 is equal to f of 1 minus 1, and that's less than or equal to 0, because again, f maps into 0, 1, and if I subtract 1 from that, then I'm going to have a value between minus 1 and 0. So if either g of 0 is equal to 0 or g of 1 is equal to 0, we have a fixed point for our function f. Otherwise, if these are both non-zero, then g of 0 is positive and g of 1 is negative. And this is precisely what we have for Bolzano's theorem applied to g. So we have g of 1, just to make it precise, times g of 0. So one is positive, the other is negative. The product is negative. And so by Bolzano's theorem, there exists some point, c, lying between 0 and 1, such that g of c is equal to 0, and that in turn implies that f of c is equal to c, and we have a fixed point. I'll end with two further results, the first of which, theorem 429, will use both the extreme value theorem and the intermediate value theorem together in its proof, essentially giving the combination of these. And the last will say something about a partial inverse for the intermediate value theorem. So in this case, in 429, we say we have a function again from some closed bounded interval to the reals. The function is continuous, then the image of the function is an interval. So that might just be a single point, so you could imagine a constant function, but what we mean by image is just the set of f of x as x ranges across the domain of f. So as a proof, we can say it perhaps more quickly in words than I could write it down, but I will take the time to write something down. But the extreme value theorem applies in this context just the same. We have a closed bounded interval, f mapping from that. So f attains a minimum and a maximum on that domain. And so what we have, using the same notation as in the previous video, we know that there exists x little m and x large m, which lie inside the interval, inside the domain of the function, so that the function is bounded precisely. So of course, since x little m is inside the domain, this is inside the image, and similarly, so is f of x big M. So these are giving us the bounds of the interval. So we're claiming that the image is some interval, and now I'm going to claim that the interval is the interval between f of x little m and f of x capital M. So I'm going to assume here that x little m is less than x large M, but almost all cases will be caught by this, or the equivalent case with the inequality reversed. So remember, the continuity is defined at a point, and we say that a function is continuous on an interval if it's continuous at every point in that interval. So we know that f is continuous on its domain AB, and xm and xm lie in AB. So f is continuous on the potentially smaller interval between these two xm's, so x little m and x capital M. But now we have these as the extreme values if we apply the function f. And the intermediate value theorem will tell us that for any point lying between the extreme values, f of x little m and f of x large M, we can find some point in the domain achieving that value. That will flesh out the full domain between those two extremes. So keeping notation consistent, if we take some y0 lying between those extreme values, then there exists some x0 lying in the domain. In this case it will be the smaller domain, although that is a subset of the larger domain between A and B, such that f of x0 is equal to y0. And so that completes the proof of 429, because that fleshes out the full interval for us. Now to end, I want to say a few things about theorem 4210. The conclusion of this is that f is a continuous function. So unlike what we've had previously, we've always taken f to be a function from some interval to the reals and assumed that it was continuous. Here we're taking f to be some function from a interval to the reals, and the conditions are that it's strictly increasing. This is essentially making it one-to-one. We can do something similar for strictly decreasing functions, but we care more or less about one-to-one. So if you need to recall, a function is strictly increasing, it means that as long as c is less than d for any values, then the image of c is less than the image of d. We have a definition of increasing, so remove the word strictly. If c is less than d implies f of c is less than or equal to f of d. But in this case I want one-to-one, so I want strictly increasing. The other condition, and quite a natural one for continuous functions, is that the image of f is an interval. Now we saw in the previous theorem that, of course, if f were continuous, then the image of an interval is an interval. So here's a graph of a typical situation. So we have the domain between a and b, and we have a strictly increasing function whose image is an interval. Part of the intuition for why this is true is that if you had any sudden jumps where you would have a break in continuity, or at least an intuitive break in continuity, then you would have a gap in the interval over here, so it wouldn't actually be an interval. So requiring it to be an interval is in a sense ensuring that there are no gaps, and requiring that it's strictly increasing is also ensuring that if I did have a gap over here, breaking continuity, it wouldn't somehow be filled in later as the function decreased and filled in that part of the image. So the way that I'll proceed with the proof is I will take some point in the interior, so I'll take a point C, and I'll show that the function is continuous at C. There's a little bit extra to do then by taking one of the endpoints, but nevertheless I'll take some point C and the rest I'll leave as an exercise. So using the epsilon delta condition for continuity, what we need is if we're given some epsilon greater than 0, we must show that we can find, or show that there exists some delta greater than 0, such that x minus c less than delta and x lying inside the domain of the function implies that f of x minus f of c is less than my epsilon. And actually in this setup, with my strictly increasing function, this is not necessarily a difficult thing to do. So I'm focusing here on the epsilon. That's what's given to me. So I'm considering f of c. So let me graph that approximately by I. So f of c, the graph is going to intersect here roughly. And taking plus and minus epsilon, I'll take a fairly generous epsilon in this case. But just to be indicative, we could take some plus minus epsilon. So this is plus epsilon minus epsilon. I want to ensure that my image of my function, that I can find some delta which sends the interval around c, between c minus delta and c plus delta, entirely between these two dashed, quite wavy, but ideally straight dashed lines. So part of this is because it's a one-to-one function, I can take my f of c plus epsilon and map it back down. So these lines are not particularly straight. I can take my f of c minus epsilon and I can map that down as well. So these are essentially pre-images. And then whatever is the smaller of these two values, so in that case it's this one here, the pre-image of f of c plus epsilon, then I can take that to be my delta, and I get a little domain whose image lies entirely between the two dashed lines. So let me make that precise. I want to take a lower value, I'll call it a prime, and a upper value here, which I'll call b prime, and then I'll take the smallest distance, either absolute value of c minus a prime or c minus b prime, as my delta. So we let a prime be such that this is related to the lower value, so that will be f of c minus epsilon. So I want f of a prime to be equal to potentially f of c minus epsilon, but if epsilon is very large, I might not be able to find such an a prime. So in that case, I would take the value of f of a, and so I actually want the maximum of these. In either case, a or something less than f of c, these are all going to be values for a prime which are less than c. And similarly, I'm going to take b prime such that f of b prime is the minimum of f of c plus epsilon or f of b, just to make sure that the value f of c plus epsilon is not so large as to exceed f of b, and therefore I wouldn't have a b prime. So now we let delta equal the minimum of c minus a prime or b prime minus c, and the way that these are set up, these are both positive, and the rest will follow. And primarily because the function is strictly increasing, we know that as long as we understand the endpoints, so the c minus delta and the c plus delta, then we understand a bounded condition for everything that lies between those values.